Good morning.
Good
Good
morning.
morning. How are you doing?
We are fine, sir.
Yeah, fine, sir.
All right, good. Thanks. Can you see my screen?
Yes, sir.
Yes, sir.
Okay. Good morning once again. Last week we looked at the course. Yeah, hello. Last week we looked at the course outline, the assessment structure, and some expectations. So I basically took you through the course outline and what you are expected for this course and the general direction of the course. Today we are starting lecture one, which introduces the foundation of digital electronics, introduces the foundation of digital introduces the foundation of digital electronics. So by the end of today's lecture, you should be able to explain what or know what digital electronics is, distinguish between analog and digital quantities, give examples of analog and digital systems, explain why digital systems are widely used, identify some disadvantage of digital system, and also mention some common logic families such as TTL, CMOS, DTL, and the rest. Now, what I want you to know is that you do not only have to memorize definitions, because I want you to understand the meaning using real life examples and application. Like mobile phones, computers, watches, speedometers, microphones, temperature sensors, and the rest. Do you get it? Good. So now, let's start with this. Now, digital electronics as a course or a subject of it, digital electronics. Now, digital electronics basically refers to electronic circuits and systems that operate using digital signals. Electronic circuit that operate using digital signals. Now, these signals are usually represented by two states. Most of the time, they are represented by using two what? Two states. Two states. So you can have a low and you can have what? A high. You can also have zero and you can also have what? One. That is what it means. Now, the reason digital electronics is very, important is that it forms the basics or the foundation of modern computing. How do we call it? And communication system. So, without digital electronics, basically, we will not have modern computers, mobile phones like digital cameras, smart TVs, routers, memory cards, calculators, microcontrollers, and many other medical devices. So now what it means is that in computer, the CPU mostly process the digital data. The memory stores the digital data. Then we have a hard drive or maybe an SSD that stores digital data. So in a mobile phones, for instance, your voice, let's say message, text message, and videos are mostly converted into a digital form before they are processed and stored and also transmitted. You understand? Good. Now, uh, uh, electronics is basically a branch of science and engineering that is connected or concerned with the behavior and movement of electrons, especially in devices such as diodes, let's say transistors, integrated circuit, and so on and so forth. So when we say digital electronics, we mean the part of the electronics where information is processed in a discrete form. Where information is processed in a discrete form. In a discrete form, where information is processed in a discrete form. But we can say that digital electronics is a branch of electronics that deals with processing of information that are represented, in a discrete form or maybe discrete values. And these are some of the examples that we just spoke about. Computers, where we have the central processing unit, the memory and the storage, the mobile phones, home appliances, like microwave, washing machine, smart home devices, automation, or in terms of automation, we have the engine unit, infotainment system. In terms of medical devices, we have imaging equipment, we have patient monitoring devices, and we have diagnosis tools. So a computer is also a digital system because it takes an input from a keyboard or a mouse, process the data in the CPU, stores the information in the memory, and also produces output on the screen. So you have input that runs into a processor or processing, then it comes to an output. So this simple input processing output idea appears in every digital system. Appears in every digital system. Now, so that we've talked about this one already. Now, there are two forms or numerical representation of analog representation and digital representation. Now, before we move to digital systems, there were analog systems. So now we look at the distinction or the difference between analog system and digital system, and also what informed decision for us to move toward digital system. So now we are saying that there are two main forms of numerical representation: analog representation and digital representation. Analog representation and digital representation. Analog representation and digital representation. Now, in analog representation, we have a quantity that is represented by a continuous. The word is continuous, varying physical quantity, such as voltage. Example is a voltage, current, sound, pressure, temperature, or meter. They are all analog representation. Now, example, if I take a room temperature is analog. Why? Because it can take many values. It can take many values. Room temperature is analog because it can take many values. Because I can basically have 25 degrees Celsius, which can also change to 25.1. I can have 21, or let's say 25.15. I can have 25.157 degrees Celsius, meaning that the temperature values are increasing. And this is what an analog is analog because it takes many values within this particular range. Now, the human voice also, for instance, in air is also analog. Why? Because the sound pressure changes smoothly with With time. Traditional speedometers, which have the pointers, it's also analog. So in our car, you see the traditional speedometers with those kind of needle pointers. It's analog because the pointer can move smoothly from one value to another value. From one value to another value. So that is what analog. Sorry. What is it? You put it there. Check. Have you seen it? Have you seen it? Analog. Now, we also have, so let's say in digital, let's come to digital representation. In digital representation, quantities are represented using symbols or digits. So here we use symbols and digits. The value changes in step, not smoothly. So here it is not continuous, it is not smooth. You understand? The value changes in what? In step. So now example is basically, who can give us an example of a digital system? Can someone give us an example of a digital system? Example of a digital system.
Sir, please, can we say the betting app?
The betting app.
Yes, please.
Digital system. Betting app. No. Betting app.
Please, I would say the counting machine.
The counting machine, yes, the counting machine is a digital system. Yeah, counting machine. What again?
Yeah, what of the calculator?
The calculator is a digital system. That's correct.
Mobile phones.
Mobile phones are digital systems. What again?
ATM.
ATM machine is a digital system. You understand? Good. So this counting machine and the ATM machine, they are all digital systems. Let's say a counting machine, for instance, it's a digital system. Why? Because it deals with discrete values. It counts objects one by one. It can count one. It can count two. It can count three. It can count four. But my question is that, can it count 1.2? Can the counting machine count 1.2?
No, sir.
No.
Can it count 3.7?
No, sir.
No. So that makes it what? A digital system. It is discrete. It only counts discrete values. It counts objects one by one. 1, 2, 3, 4, and so on. It does not count continuously, like let's say 1.2, 1.5, and so on. So the counting machine is also, but for the betting app, maybe technically we can argue out. Technically, we can say it's a digital system, but sometimes someone can also argue it way out that it's also an analog system. But in a digital system, I can look at it as, let's say, because maybe it runs on maybe a mobile phone, because it runs on a mobile phone, or maybe it runs on a computer, and it processes the information digitally. You understand? So yeah, you can argue depending on how you explain it. Because if I am saying it's a digital system, then I can say that maybe because it runs on a mobile phone or a computer and it processes information digitally. You understand? Good. So example of this, all that you have said are correct. The ATM machine, the digital watches, the mobile banking app, counting machine, computers, traffic controllers, they are all digital system. A digital watch, for instance, may show 10:15. Then it can show 10:16. 10:15, 10:16. It does not show all the infinitely small changes between 2 minutes. We can also have what we call a 10. We can also have what we call a 10 position switch. A 10 position switch. A 10 position switch is also digital because it has fixed positions. It has fixed positions. You see, good. So a 10 position switch is a digital because it has, fixed position. Position 1 can have position 2, can have position 3, and so on. So on this slide, the take home is that analog. On this slide, the take home is that analog is continuous. and digital is discrete. Like, what you have to know is that analog is continuous and digital is what? Is discrete. It's discrete. It's discrete. If you look at the waveform of analog, it changes smoothly. So analog, we will look at the waveform, it changes smoothly with time, continuous like this. And that of discrete or digital looks like this. Looks like this. Digital changes with what? With time. Like that. Good. Now let's come to analog systems again. We are saying that it's a quantity represented by voltage, current, or meter movement that is proportional to the value of that quantity. Example is what we listed. The microphones, the automobile speedometer, the room thermostat, the room temperature, and all that. All these are what? Analog system. The characteristics or the features is that they can vary over a continuous range of values. Over a continuous range of values. So it means that current that is flowing out of an electrical outlet, is it analog or digital? Current flowing out of an electrical outlet, is it analog or digital? Who can tell us?
Analog.
It's
Yeah,
analog. It's analog. This is because
Analog.
the current
Yeah.
what varies continuously with time. It varies continuously with what? With time. Varies continuously with time. Especially alternating
Sir,
what?
please, so,
Hello?
sir, please, so can you say that the analog starts from 0 upwards?
Can you say that word?
With analog, it starts from 0 upwards, like from low to high.
No, it doesn't mean that analog basically start from, how do we call it? Start from zero. You understand? Huh?
Okay.
This is
Okay.
basically the signal, how do we call it? Signal representation. You understand? And every
Okay.
signal representation like this, basically the origin is what? Is zero. But it doesn't mean that analog start from what? Zero. Analog does not mean it start from zero. Analog means that the value can change continuously within a range. It may start from zero, but it can also start from any other what? Value. Let's take the room temperature. Does the room temperature always start from zero?
No.
No. It doesn't always start from zero, but it is analog. It can start from any degree. It can start from 25, can start from 25.1, 25.15, and all that. This is analog because the value changed smoothly. It did not need, doesn't need to start from what? From zero. That's what it means. Okay. Good. Yeah. Then we come to digital representation. The quantities are represented not by proportion quantity, but by symbols called what? Digit. And this, symbols or digit that we're talking about is zeros and what? And one. Systems process zeros and that of what? Of one. So it processes zero and what? One. So a digital system manipulates information that is represented in a digital what? Form. Example is what we said from the beginning: computers, calculators, digital video equipment, modern telephone system. All these are what? Analog systems. So it means that the value changes in a discrete form. The value changes in what? Discrete form. Values changes in discrete form. So the major difference between analog systems or analog signal and digital signals is that analog is continuous in nature, varies continuously in nature, and digital is what? Discrete. Now, if we say that the value changes in a discrete step, it means that the values changes, basically refers to variables that transition between distinct separate values, like integers. So it means that at specific intervals, so specific at specific intervals, rather than changing smoothly over time. Okay. Please, when you have any question along the line, kindly ask, because if you raise up your hand, I will not be able to see. So when you have any question, you can come in at any time. Feel free. Okay. Then we look at the waveform representation. The waveform representation of analog and digital signal. The waveform representation of analog and digital signal. Now, so let's look at this diagram. We have analog signals and we also have digital signals. Analog signals and we also have digital signal. Now, the analog, you could basically see that the analog is moving continuously with respect to time, moving continuously with respect to time, moving continuously with respect to time. We also have the sample time, the sample time, the time at which you sample a particular value, the sample time. So if you look at this becomes okay. This become an amplitude. This is an amplitude. This is an amplitude. This is an amplitude. This is an amplitude. You understand? So we have different amplitudes that are sampled at a particular point in time. The amplitude are sampled at a particular point in time. So that is the representation of an analog signal. The representation of an analog signal. The representation of an analog signal is is continuous. Now, when we look at that of digital signal is discrete. It's steps. The reason why we say it is step is that it's like a normal, practically it's like a normal, how do we call it, steps that we normally would climb, understand? So that is with the digital signal. And that also moves with respect to time. That also moves with respect to time. So this is a diagram that depicts analog signal representation to that of digital signal. Analog signal representation. Okay. Analog signal representation to that. Analog signal representation with that of digital signal representation. So that is what I have explained. Analog signal changes smoothly. It is a smooth transition, continuously. It does not jump suddenly from, let's say, one value to another. So at every point in time, it can have values. At every point in time, it can have value. And this is why we say that analog values are continuous. The signal can take many possible values between points. Many possible values. Many possible values between the point. Many possible values between the point. But when you look at the digital signal changes in step. It changes in in steps. It changes in step. It does not take all the possible values. It moves from one level to another level. It moves from one level to another level. So it can move from 1, can move from 2, 1, 2, 3, 4, 5, and 6. Now, if you look at an analog signal again, the sample times is also there. The vertical line basically marks the sample time. It shows the movement when the analog signal is measured. The movement at which the analog signal is measured. Now, since the computer system cannot store every infinite value of analog signal, what happens is that it takes measurement. You kindly mute your microphone. It takes Please kindly mute your microphone.
Richard,
Richard, please. Oh,
Richard,
ah,
Mute.
Okay. So what I was saying is that since the computer system cannot basically store every infinite values of analog signal, it takes the measurement at specific times. And this measurement point is what we call the sample times. The measurement point is what we call the sample time. So let's say, for instance, when you are recording a voice, we have voice in the air, then to the microwave, and they are sampled. So the digital signals is produced by taking the selected values from the analog signals and representing them using what? Digit. That is what it means. That's what it is. Please, any question before I move to the next slide? Let's all try to understand and also ask questions so that it helps all of us. Any question here before I move on?
No, sir.
Yeah.
So the points that the digital signals also move is also considered to be amplitude, right?
Now, okay, amplitude means the maximum threshold. You understand? So if I draw a waveform like this. This part is what we call the amplitude. So it doesn't mean that amplitude can only be, let's say, high. We can have a minimum amplitude and we can also have a maximum amplitude. That is what basically it means. Yeah. So those are what the amplitude. Any other question? Any other question?
Sir, please, so does it mean that the digital waveform always move like the square or rectangle, and
yes,
the analog like the sine waveform like that?
That is correct. That is correct. So good. Okay. One distinction between analog and digital signals in terms of waveform is that analog signal is in the form of a sine wave. Or can I say sinusoidal? Sinusoidal wave or a sine wave. And digital systems or digital signals are in the form of a discrete.
Sorry. So in your question is anywhere we see the rectangular or square waveform like that, we can identify it as digital.
Square or rectangular, good.
Okay, thank you.
Good. So in terms of waveform representation, analog is in the form of a sine wave or a sinusoidal wave, whilst discrete digital signals are in the form of a square wave or a rectangular wave or shape. That is what it means in terms of waveform. Now let's come here. This is very interesting. If we were supposed to be in class, you do this, then I'll come round and I'll mark. But now let's all discuss it together. Let's take the first one. Which of the following involve analog quantities and which involve digital quantities? Your answer, when you mention any answer, you need to be able to justify by saying the reason why you feel that it is analog or the reason why you feel that it is what? Digital. Let's come to the first one. Current flowing through out of an electrical outlet. Is it analog or digital?
It's analog.
Why?
It's analog because the current is not static. It's not discrete. It keeps changing.
It keeps changing. Okay.
Yes. It can change at any point in time.
Any point in time, that's correct.
It can be low, it can be high as well.
Okay, that is correct. So it is analog because the current changes. It varies continuously with time. A basic example is an alternating current. Alternating current. That's correct. That's perfect. The second one. Temperature in the room.
Analog.
Why analog?
It is continuous. It changes.
It continues.
Yes.
The temperature of a room is not static. The temperature of a room
is not stable.
It's not stable. It changes
It changes smoothly.
It can
at any point in time.
It also changes smoothly.
Smoothly. That is also correct. Good. The third one. Sun grains on the beach. Is it
digital?
Okay, why digital?
It's static. It can move. It can change as compared to the analog.
I understand, but your explanation is
Sir,
quite
Doc,
analog. Uh-huh.
it can be counted in whole numbers.
This is what we want to understand. It is discrete because in terms of counting sense, you understand. This one doesn't. We can't say this one changed. This one. This one is not like it's something that what is countable. So it's counting sense because the number of grains is countable. Can you have one grain? Can you have one grain?
No.
Yes.
Yes.
Yes, sir. Yes, sir.
Can you have 2 grains?
Yes, sir.
Please.
Can you have
Yes,
3
sir.
grains?
Yes, sir.
Yes,
Can you
sir.
have 2? Can you have 2.5 grains?
No.
No,
No,
sir.
sir.
No, sir.
No.
Yes.
No. So that makes it what a digital system, a digital system. Because in counting sense, because the number of grains is countable, you understand? It is digital. You cannot count 2.5
Grains.
to 1.5. Okay, the fourth one, sorry. Automobile speedometer.
Analog.
Digital.
Analog. Analog.
Analog.
Okay, so if it's analog, why analog? If it is digital, why digital?
Speed changes continuously.
Yeah, it goes up and it comes
Yes,
down.
it goes up and it comes down. It's
You
true.
can have a low speed.
Yes,
And
when
you can have
you down, the speed comes down.
120,
Okay,
120,
okay.
and the rest.
I think
But
Let's
it
say
moves.
the speed can be at a particular time and moves up again. So I would say it's digital.
you will say it's digital. Okay.
It's analog because it moves continuously to represent speed.
Okay, so do we have digital speedometers?
Say yes, right
We
now.
do. Now
The
we do.
electronic cars that are coming, they have digital.
Okay, so now the new cars or the modern cars that are coming, they have digital speedometers, right?
Yeah.
Okay,
Yes.
good. Okay, good. But in this case, okay, so then we need to, make it very clear that, okay, maybe a traditional speedometer, you understand? A traditional speedometer. But in this case, we are talking about traditional speedometer, you
So
understand?
it's analog.
It is analog because the pointer basically moves continuously. If it is a digital display speedometer, it is different. Then the display is what? Is digital. But from this, what we have basically automobile hot speedometer. It is usually treated as what? As analog. Usually treated as analog. The last one, 10 position switch. The last
Analog.
one.
Digital.
Digital.
Okay. This analog. What is your reason? If it is digital, what is your reason?
It's digital because it has only 10 distinct positions.
It has only 10 distinct positions. Okay,
Yes.
let's hear those who are also saying it's analog. Okay, analog. Can you tell us the reason why? Just feel free. Let's feel free.
Yeah, so say I also go for the analog because
Okay.
it can move from 1, 2, 3, 4, all the way to 10, and therefore it's a digital one.
No, you said analog.
Yes,
Oh.
therefore
From the beginning you said analog. Now, which one? Your analog has changed. Your definition of analog has now changed.
It's a digital one.
Digital one. Okay, so it can move from one because the positions are how do we call it? Are fixed. So if it's a 10 position switch, we can say 0 to 9. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So it is what? It's a digital what? It's a digital because it has fixed what? Position. Sorry. Fixed what? Position. So you notice that sometimes physical quantities may be analog, but the display may be what? Digital. For example, speed. Speed itself is continuous, but a digital speedometer display it in a discrete numbers. So that is all about this particular slide. Okay. Let's move to a little bit detail about digital system. So the digital systems is a combination of devices designed to manipulate logical information or physical quantities that are represented in a digital form. They are represented in a digital form. Digital form. Example: computers, calculators, audio, systems, and other. These devices are most often electronic, but they can also be mechanical and also magnetic. So when I speak now, my voice in the air is analog. When I speak now, my voice in the air becomes what? Analog. A microphone basically converts this sound into an electrical signal. So if we record it using a phone, the phone will rather convert the analog signal into digital data. When we play it back, it converts the digital back to what? Into sound. So the real world, we have sound that goes into, let's say, a microphone. Then we have something that converts the analog to digital. We call it the ADC, the analog to digital converter. We will look at that. Then the signal is being processed. Then it changes digital to analog converter before it speaking. We will look at that. Okay. So the digital systems include computers, calculators, which we've just spoken about. The analog systems contains devices that manipulate physical quantities that are represented in what? Analog form. We have looked at the representation of analog signal. These quantities can vary over a continuous range of what? Of values. Example of analog systems are audio amplifiers, magnetic tape recording, and playback equipment. These are all analog systems. Okay. Now, digital systems are easier to design. So these are some of the advantages of what? Digital system. Advantage. These are some of the advantages of it. It is easier to design because why? On only two states. Either it is working on 0 or it is working on what? On 1. And this makes analysis and design easier compared with what? Circuit that must handle infinitely many values. The second one means that easy information storage. What does it mean? The information can be stored in a memory. So we can have a memory that can store the information. We have RAM, read access memory. We have the ROM. We have the flash drives, the USB drives, the SSD, and all the memory cards. So it is easier for you to store information. Then the next one is greater and precision are accurate. Digital systems can represent and process data with a high accuracy, high level of accuracy, high level of precision, depending on the number of bit that is being used as compared to the analog systems that we have. The next one is operation can be programmed. A digital system can be programmed. How? It means that the hardware that we have, the same hardware can perform different tasks depending on the software that is being used. Let's come to practical example. Let's say your phone. Your phone can be a calculator. At the same time, your phone can be a camera. At the same time, your phone can be, let's say, a music player. At the same time, your phone is let's say, a communicating device. At the same time, GPS, because its operation is what? Programmable. Because its operation is programmable, we have different applications that are being or can be run on it. The next one, digital circuits are less affected by noise. Because in digital system, the circuit only needs to decide whether a signal is 0 or it is 1, or whether it is closer to 0 or it is closer to 1. So the small noise may not change the final decision of the system or the digital, the output. The last one is that it is more digital circuitry can be fabricated on integrated circuit chips. It means that digital signals can be integrated into a small chip. Now we have a lot of integrated circuit or chips, and this is why modern processors can contain billions of let's say transistors, billions of transistors. So these are some of the advantages of
Sir,
digital systems.
please.
Uh-huh.
So how does the discrete values, I mean the zeros and one, make the digital systems easier to design?
How does which one?
Go over that one. I mean the how does the discrete values make the digital systems easier to design?
Okay. So it is basically operating on two states. It is basically what operating on two states. Either it is operating on 0 or it is operating on 1, or either it is operating on the on state or it is operating on. Let's imagine the switch in your house or in the switch in our homes. It is either I put it on, the light on, or I put the light off. The fan, either I'm putting it on 1 or I'm putting it on maybe 2 or I'm putting it on 3, or high or a low. So the discrete values make the digital system easier to design. Why? Because the circuit does not need to understand every possible value. It only needs to decide a few fixed states, and the state is zero, is low or high, and the state is on and off. So it is easier to do what? To design. Imagine the fan. You want to put the fan on 2.5. Imagine you want to put it on 2.5. It will be very difficult for you to do that. Or decide two fixed states, which is 0 and 1. 0 and 1. Low or high. Off or hot or on. And that is what it means. For analog, a voltage may be 0. You can have 0.1, you can have 0.25, you can have 0.9, you can have 1.34, you can have 2.64. So imagine these different values that are changing continuously. And the one that I'm having only two states, either on or off, either 1 or 0, either low or high. Which one will be easier for me to design? Which one will be easier for me to design?
The 0 and 1.
The 0 and 1. Because I need only two states. So the circuit does not need to know whether the voltage is exactly maybe 3.1, 3.5, 4.8. It simply treats all of them as logic 1. All of them as logic 1 or 0. So the digital design is easier because we reduce many possible values into a smaller number of states. So instead of, let's say, designing a circuit to handle infinite values or continuous values, we design only recognize 0 and 1. Very easy. Very easy. Now, there's a strong statement here. There is really only one major drawback when using digital technique. Now, the major drawback of digital technique is the real world. Now, the real world is analog. The real world is analog, even though we are operating in a digital world. But the real world itself is analog. Let me explain further. Temperature, pressure, sound, light intensity, speed, distance, all these are analog. All these are analog. But the digital systems need digital data. Therefore, what happens is that we must convert real-world analog signals into digital form before we can process them. I'm taking it again. I'm saying that things like temperature, pressure, sound, light intensity, speed, distance, and all of them, they are analog. But the digital systems need a digital data. Therefore, we need to convert the real world analog into a digital form for processing. It basically means that I have analog input that maps means that I convert to digital. From here, it should process it digitally. Then it needs to convert it back. Convert back to analog. Because if it doesn't convert it back to analog, it will be very, difficult for you to interpret what the output. So it needs to convert it back to analog. So let's say another example. Let's say in a music, when you are recording a music, the singer voice, the voice is basically purely analog. Our voice is purely analog. The microphone first captures it. Now the system will convert it into a digital form. The computer, which is a digital machine, processes or stores it later. Then the digital signal is now converted back to what? Analog, so that the speaker can produce what? A sound. If not, basically you will not be able to hear. And this is the reason why the conversion of this particular thing adds cost and also complexity and also delay. Because if it is a one-time thing, then that is fine. But because it is going through a lot of processes or some processes, we need to purchase some hardware, which brings about cost. The system becomes a little bit complex. And now there is also a delay from the conversion of one, to another. Because I have an analog to digital converter that converts the analog to digital. Then I also have a digital to analog converter that converts the digital back to analog. So the ADC and that of the DAC circuit requires design. It requires power. It requires time. It also requires money. It requires money. So when dealing with the analog input and output, 3 steps must be followed. First, convert the real analog input to what? A digital form. Then the signal is being what? Processed. Then convert the digital output back to what? Analog. So we have ADC and we have what? DAC. Analog to digital convert. Then we have DAC. Convert digital back to what? To analog. Digital back to analog. Okay. So example of the analog, the human voice, the analog amplifiers, they are all analog. Digital, computers, CD drives or CD, they are all DVDs, the phones, these are all what digital system or digital stuff. So now, this particular slide also means that the digital system may require more bandwidth. More bandwidth is more space to carry the same information. And this can only happen when digital representation requires extra bits. When you are doing some coding, when you are doing some synchronization and all that. However, the digital systems are still preferred because they are easier to store. You can easily store the digital information, process, copy, encrypt, compress, and also transmit it reliably. So the need for conversion between analog and digital forms of information can be considered a drawback because of added complexity and cost. Added complexity and cost. The extra time required to perform this conversion. This is where the delay also comes in. Aside that, perfect. So up to this point, the key message I'm trying to proclaim is that analog systems use continuous signals, while digital systems use discrete values. Digital systems are more suitable for modern computing because information can be stored, information can be processed, you can program the information, and you can also transmit them more reliable. So here, what I need you to understand here is that what is the major difference between analog and digital system? If I ask you, give me one example of analog quantity, give me one example of digital system. Why is it that digital systems are less affected by noise? All these things, you should be able to say it. So this is a table that shows the distinction or the difference between analog and digital systems. We have studied this, but let's quickly go through this. In terms of signal representation, Analog represent physical measurement. Digital are discrete and generated by digital modulation. In terms of waves, sine waves and square wave or rectangular wave. In terms of representation, it is continuous. This one is discrete. In terms of data transmission, it is affected by noise during transmission. We have a lot of noise in analog system. But with digital system, they have been programmed in such a way that they are robust, they are immune during transmission. Response to noise. It is more likely affected by noise, but digital systems are less affected by noise. Analog systems in terms of bandwidth or capacity, it has a less bandwidth, but digital systems have more bandwidth. More bandwidth means that it can carry out the same information or say more information. It's like, let's say if we have a classroom that can take, let's say, 20 students. A classroom that can take 20 students, 20, student. Let's say if you bring a 50 student inside that room, the room becomes very congested for the student, meaning that small. But if we have even a class that can take 100 students and you bring 50 students inside, the room, then it means that there is still space or capacity that you can carry more information. And the more bandwidth you have, you can transmit more information at a time. The more bandwidth you have, you can transmit more information. So the larger the class size of student, that's what it means by bandwidth. Then memory, it can store data in the form of a wave signal. Digital can store data in the form of binary bit, which is in the form of zeros and ones. And examples is what we have listed or we have studied in the previous slide. Voice, analog. When you come to digital, we have computers and we have CDs and we have DVDs. This is a summary of what we have studied. So, before I come to the logic family, any question? Before I come to the logic family, any question? Any question?
Good morning, sir.
Yeah, good morning.
Sir, please, so as we are having class now, will you term it an analog or digital?
Hello.
Hello, sir.
Yeah.
Please, I wanted to find out whether this class we are having now, will you term it as an analog or like digital?
Okay, good. Now, what is happening? It is going through a series of process. That's what we are saying. My voice is analog. So it is a process. My voice is analog. The class itself is not simply analog or let's say digital. But it depends on which part of the class you are talking about. You understand? Your voice in the classroom, we have studied that our voice is what? Analog. So when I'm teaching or when you are teaching, unless a student or you have audience that are hearing your voice travel through air or space as a continuous sound wave. So that part of it is analog. Only that part of it is analog. The person or the presenter, the person who is speaking, that part of his session is what? Analog. The voice is analog. Now, this is analog. Why? Because the sound changes smoothly and continuous. Now, in terms of the number, when you count the number of students in the class, I can count one student, I can count two, I can count three. Now, when I go onto the platform, the Zoom platform, and I check, I can know the number of students there. Let's say 80 number of students, but I cannot see 80.5. I cannot see maybe 3.4. This means that this is digital because able to count whole numbers. So the sound of the class is analog, but the number of students is digital. That is the second process. Then 3, online class. The online class is digital after conversion. Because if the class is on Zoom, or let's say on WhatsApp, or let's say on Teams, or let's say Google Meet, your voice starts as analog, but the phone or your computer that you are using, some of you are using computers, some of you are also using phone. Now the phone or your computer will convert it into digital data before sending it through the internet. So the process becomes what? This is the process. So what you just said, the process is analog. It comes to microphone, then digital. So a physical classroom discussion that we are having, is mainly analog because the voice are continuous sound wave. But when we count the students, record attendance, when I take, notes, or when I transmit the class online, those parts becomes what? Digital. So the voice is analog, attendance is digital, the online class is digital. So it is not only, you cannot term the whole session as what? As analog or digital. It is a process that it is going through. So at each point in time in the process, you can determine whether this step or this process or this stage is analog or digital. But in the whole, you cannot describe the whole system as what? An analog process or a digital process.
Okay, sir. Thank you, sir.
You're welcome. The logic family. Okay.
Sir, please, good
Yeah.
morning.
Yeah, good morning.
So there's this thing that normally happens when a mobile phone is by a radio, and then yes, sir. And then there's an incoming call. You normally hear a certain sound back, a feedback from the radio, pop, something like that.
Mm-hmm.
Sir, please, what causes that?
Okay, so this is a different concept when we are looking at maybe wireless communication. Now, a mobile phone call uses both analog and digital part, but the mobile phone system is mainly treated as a digital system. Now, when someone calls your phone, the signal basically reaches your phone through what we call radio waves. Now, the radio waves in the air they are basically electromagnetic waves, electric and magnetic wave that is being put together. So they are analog in nature because they vary continuously. But the information carried by the mobile phone is what? Is digital. It's digital. So the radio waves is analog as a physical signal, but the information inside the mobile call is what? Encoded and processed what? Digital. So you can have an incoming radio signal, what is analog. The call information or the number or the voice or the ringtone from the speaker becomes what? Analog. Now, at the point to when someone is also calls or someone is calling, now the signal can interfere with that of the radio signal. And that is what basically causes what? Interference. So it basically causes what? Interference. And interference causes, it's being caused when you have, systems operating on the same frequency. When you have a system that are operating on the same frequency, there's a high level of probability of interference or signal interfering with one another. So it's like, let's say, in a class, if all students are given, let's say, a power of less than 1 watt, and they are all supposed to speak at the same time, the power is the same for all the students. You understand? The power is the same for all the students. So it can create some form of noise or some form of glitches or some form of interference within the system. That is what this one basically also means. Are we okay?
Yes, sir.
Okay. Now the logic family. We'll close very soon. The logic family. Now, the logic family, now we understand digital systems. We know how digital circuits are physically implemented. Now, the logic family basically means, or it's a class or a group of electronic circuit that is used to implement digital logic function. We have the basic digital logic function that we'll look at, the AND, the OR, the NOT, the NAND, and all the NOR. We'll look at them. In a digital electronics, we do not only talk about zeros and ones abstractly, but we must also build real circuits that can produce 0 and 1 using transistors. We need to build them. Not only transistors, using diodes, using resistors, using integrated circuits. Different methods of building these circuits is what we call the logic family. Different methods that we use to build this circuit is what we call the logic family. The logic family. The first one, we have what we call the emitter-coupled logic. Now, with the emitter-coupled logic, let's say when engineers choose a logic family, you first need to consider the speed. Very important. When you are choosing a logic family, you need to consider what the speed. You need to consider power. You need to consider parking density. You need to consider what we call fan in, fan out, and the others. Now, these are very important. Now, with the emitter-coupled logic, the emitter-coupled logic means that the emitter, it means that it uses what we call a bipolar transistor, basically a transistor, bipolar transistor. And the key idea is that the transmission are not driven, into what we call saturation, because they avoid saturation and they can switch very, very hot fast. Most of you might have seen a transistor before, or maybe know about transistor. It's just a semiconductor device that function either as, let's say, a switch to control the flow of electrical current. That is basically a transistor. It's a semiconductor device. It can amplify or switch electrical signal and also power. So now, because they avoid saturation, they can switch very hot fast. And one main point about emitter-coupled logic is that it is very fast, but it consumes a lot of power. Consumes a lot of power. Very fast. So we are basically getting a trade-off of speed, faster speed, of with what how do we call it, consumption of power, which comes in the form of also cost. Then we have the resistor transistor logic. This basically uses what we call a resistor. What is a resistor? A resistor is a passive terminal or electronic component that implement electrical resistance as a circuit element. That is, it resists or reduce the flow of current in a circuit. Resist the flow of current in a circuit. It uses resistors as the input network and bipolar junction transistors as a switching method. The main important is that it is simple, very simple to use, but it has high current dissipation when the transistor begin to conduct. So high current dissipation. High current dissipation when it begins. Then we have that of a diode. Diode allows current to pass through in one direction and blocks current in the opposite direction. This diode performs a logic gating function. So while the transistor provides amplification, the diode transistor logic improve on the RTL and has the advantage of increase in fan in and fan out. Then we have the transistor logic. In transistor and transistor logic, both of the logic gating function and the amplification function are performed by the transistor. What it means is that it's very common in digital electronics compared to that of, let's say, CMOS. But even with that, it also consumes more power, especially when it is at rest. Even when it is not working, it consumes more power compared with the previous ones that we have used. But the TTL is what uses less power, but it's usually slower. Less power, but usually slower. Then the CMOS. Complementary metal oxide semiconductor. That is widely used. The most widely used. Processors use CMOS. Microcontrollers use CMOS. The memory devices use CMOS. Most modern digital logic gates use CMOS. And CMOS has a very high noise immunity, very robust to noise, very high noise immunity. Its power consumption is very low. And this is one of the reasons why CMOS dominates most of the modern digital electronics, because it has a very high noise immunity. It is low in terms of power consumption. Example, let's say the processor in our mobile phone, or let's say a computer, or let's say even a router, and most of this embedded system, all these are based on CMOS. All these are based on CMOS. All of them are based.
Please, is that why they have the CMOS battery?
The CMOS battery, very good. That's an excellent battery. That is the reason why we also have the CMOS battery. Very low in terms of power consumption and very high noise immunity. Very high noise immunity. Okay. Now, the main parameters you need to also consider when you are when choosing the logic family is speed. Speed, very important when you are looking at the logic family. Speed, how fast the circuit can switch between how fast. How fast the circuit can switch between zero. That is the speed. Power dissipation. How much energy the circuit will consume and how much heat is produced. Very important. This should inform your decision when you are selecting this logic family. How much energy will this circuit consume and how much heat will it produce? We have the packing density. How many circuits can fit inside one chip? How many circuits can fit inside one circuit? Inside one chip, one chip. That is the packing density. Then the fan in, fan out means the fan in means the number of input in the gate, or the number of input the gate can accept. Then the fan out means the number of other gates one output can also derive. Then we have the noise immunity. That is the ability of the circuit to resist unwanted electrical disturbance or resist unwanted electrical noise. Availability. How easy it is for you to find. How easy it is for you to use the component from that family. So a lot of people, appreciate and like buying Toyota cars, because they feel that, the components are easily to get. So a lot of people also like Toyota cars because, they feel that it is available on the market, and at any point in time, they will be able to get any part when maybe they have some of their part maybe malfunction. Then we have the frequency. That is the maximum frequency at which the circuit can operate reliably. What is the frequency at which the circuit can operate reliably? We also look at that. So before you select a particular logic family, these parameters should inform your decision in selecting that. And we've come to realize and know that the CMOS, dominate all this, how do we call it, logic family. Because it's used in microprocessors, controllers, and modern digital circuit, because it has a very high noise immunity, low power consumption. And these are the very key, parameters that needs to be considered.
Sir.
Yeah.
Please, what's the difference between the operating frequency and the speed?
Operating frequency and speed. Okay.
Yeah.
Now, operating frequency and speed. Now, from what we said, let's go back to the slide. We said the speed is how fast the circuit can switch between 0 and 1. So it means that with the speed, it is switching between what? Between states. It is switching between states. How fast a digital circuit can change from one logic state to another. So how fast can it change from 0 to 1? How fast can it change from 1 to 0? How fast can it change from low to high? How fast can it change from high to low? So the speed is usually discussed using propagation delay, because propagation delay is the time it takes for the output of the logic gate to respond after the input has changed. So immediately the input changes, the output needs to respond. And if there is a delay in response, that is what we call the propagation delay. Now, if a logic gate has, let's say, a small delay, it is a fast gate. If it has a large delay, it is a slow gate. Now, the operating frequency is different. The operating frequency means that how many cycles or how many operations the digital systems can perform per second. It is with respect to time. That's the reason why we have frequency is equal to 1 over t. So the frequency is inversely proportional to that of the period. And it is measured in what? In hertz. So hertz means 1 cycle per second. Kilohertz means 1,000 cycles per second. Megahertz means, how do we call it? Megahertz means 1 with 6 zeros. Then gigahertz means 1 with 9 zeros. Cycles per second. So let's say if you have a processor that operates 2 gigahertz, it means its clock can run, let's say, 2 billion cycles per second. So it means that the operating frequency is the rate at which the whole digital circuit can run reliably. And in terms of speed, the speed is how fast can it switch between a higher frequency. That is what it means. So because if the circuit takes too long to change its output, it means that the cycle may arrive before the previous operation is completed. So the speed tells you how fast the circuit can switch between 0 and 1, 1 and 0, low and high, high and 0. But the frequency, inform your decision in terms of the rate at which the whole circuit or system can run effectively or efficiently or maybe reliably. That is what it is.
So,
sir,
Yeah.
Can we say can the speed affect the operating frequency?
Can speed affect operating frequency? Yeah, speed. That is what I explain using, how do we call it, the propagation delay. You understand? The speed can definitely affect the operating frequency, because now, if you are supposed to, let's say, how do you call it? Okay, let me take it this one. The speed means how quickly a circuit can change its output after the input has responded. Now, if the delay is small, the circuit is what? Will the circuit be fast or low or slow?
When the delay is small,
Slow.
it will be fast.
If the delay is small, will the circuit be fast or slow?
Slow.
It will be fast.
If the delay is small, will the circuit be fast or slow?
It will be fast.
It will be fast. So if I have a small delay, the circuit will be fast. If the delay is large, the circuit will be slow. So it tells you that the speed affects the operating frequency. The frequency means how many cycles per second the circuit can run efficiently. So it means that if I have, let's say, a higher speed, a higher speed means smaller delay, which is high. If I have low speed, if my speed is low, I will have larger delay, which will lead me to what? A lower. You understand? So if I have a logic family and it has a delay of, let's say, 1 nanometer. So let's say a logic family A has a delay of 2 nanoseconds. Sorry, 2 nanoseconds. And B has a delay of, let's say, 20 nanoseconds. Which one will be faster?
A.
A will be faster. A logic family A is faster. So it means that it can operate at a higher frequency because the delay is what? The delay is what? It's small. It can operate at a very higher frequency than a logic what? B. So if the circuit is slow, it needs more time to complete one operation. Therefore, we cannot clock it too fast. If we clock it too fast, the next operation will start before the previous one has what? Finished. So that is what I mean. Very simple. Yeah.
Please, can we use an ambulance as an example?
Okay, explain that. Let's see.
So the ambulance, as it moves towards you, the pitch sound higher, but the frequency, like moving away, the frequency, you get a lower frequency.
Okay, so that is what we call Doppler effect.
Okay.
That is what we call Doppler effect. An ambulance itself is not purely, let's say, analog or let's say purely digital. It contains both analog and digital system. So the ambulance is just a physical vehicle, yes. But the system inside is what we can categorize as maybe analog or digital, depending on basically what we are discussing. You understand? So the ambulance siren is analog. The siren itself is analog because the sound is changing continuously in the air. That is when you are approaching the observer, the pitch of the sound becomes very high. But when you are, moving further away from the observer, the pitch of the sound becomes very low. So the flashing light controller is digital. So I told you that we can explain the process to know at what point is it analog and at what point is it digital. But we cannot say straight or abruptly that it's analog or it is digital. So the ambulance siren is analog because the sound will change in the air. But the flashing light controller is digital because it switches between two states, on and off. It also uses GPS. So the GPS and the electronic controller system inside the ambulance are also digital. So we can segment or divide each of the states as either analog or digital. We can definitely do that, and that is what we have done. So the analog means continuous, while the digital means what? Discrete or step. So for the process, we can segment them into what? Analog and digital. But we cannot just say that this process is what? Analog, or this process is what? Is digital. No. It has different processes that it goes through for such action to take place. Okay. Let's come to the computer system. That's our last slide, then we close for the day. It's our last slide. A computer system. We know it is made up of hardware that performs arithmetic operations, manipulate data, and also make decisions. The computer we know is very fast or faster and accurate, but it does not think by itself. It must be given instructions. Hello? It must be given instructions first. And these instructions is what we call a program. The computer needs instructions before it works. And this instructions is what we call a program. A program is a set of instructions that tells the computer exactly what to do, step by step. It must be given a complete set of instructions that tells it exactly what to do, step by step. And that is what we call what? A program. Okay, it is here. Programs are placed in the computer memory unit, binary coded form, with each instruction having a unique code. So inside the computer, the instructions and the data are stored in the binary coded form. What does it mean? It means they are represented using zeros, a combination of 0 and 1. So we have the input that goes to the CPU, that goes to the output, then the CPU also with that of the memory. Now, the major part of the computer. Let's basically use the diagram to explain this concept very well. This is basic. This is basic part of the computer system. Now, we want to look at the digital computer system. We have a data information, we have the central processing unit, we have the input, we have the control, we have the memory, and we have the output, and then we have data information. We have different, signals. We have the control signals, and we have the data information. Now, a digital computer works like this. We have the input that goes into the processing unit. So all this is the processing unit. Then we have the output. So input to the processing unit. Then we come to the output like this. Very simple. Now the input block that we are seeing there receives the data or the instructions from the outside computer. So that is your keyboard, your mouse, your scanner, your microphone, your touchscreen, your sensors. These are the input. These are the input. So the input unit is the part of the computer that accepts the data and the instructions from the user. So it is you, the user, that will feed, the system with whatever you want to feed it with. So when you type, let's say 5 plus 3 on the calculator, the keypad is the input. So the keypad becomes what? Your input. Now, we have the central processing unit. The shaded part is the central processing unit. Now, the CPU is the heart or the brain of the computer. It contains mainly the arithmetic logic unit, which is this one. The arithmetic logic unit. Which is this one. And also the control unit. Now, the arithmetic logic unit performs calculations. It performs arithmetic. It makes logical decisions. And what are these? We have addition, we have subtraction, multiplication, division. This is the function of the arithmetic logic unit. Logic operation. And the logic operations are AND, OR, and NOT. So the ALU is part of the CPU that performs mathematical. So it performs both mathematical and logic operation. So if the computer is asked to calculate, let's say 5 plus 3, it is the function of the ALU to perform the addition. Let's come to the control. The control unit do coordinate all the operations in the computer. So what does it tell us? It tells other units what to do, what time to do it, and when to do it. When are you supposed to do it? What time and when to do it? So it does not mainly calculate. Its main purpose, is to control the movement of the data and the instructions inside the computer. So it basically tells the memory to send an instructions. It tells the ALU to perform an operation, and it tells the output unit when to display what results. That is the main, purpose of what the control unit. Then we come to the memory. The memory basically stores what? Data. It stores what? Data. It stores data. Examples of this memory, what the memory stores is. It stores data. It stores programs. It stores temporal results. It can store also final results. So the memory is where the computer keeps all the instructions. All the instructions. Let's say example, if I'm calculating, let's say 7 plus 3, which will give me 10. The number 7 and 3 may be stored in the memory before the ALU adds them. So this first stored before the arithmetic logic unit adds there. Then we come to the output. The output gives the processed results to the user. Who can give us example of output device? Who can give us examples of output devices?
The monitor.
Monitor. What again?
Speaker.
Printer.
Printer.
Projector.
Project.
Computer.
Good. All these are what? Output what? Devices. All these are what? Output what? Device. So the output unit represents what? The how do we call it? The output of what? The information that has been what? Transmitted. Any question? Any question? So I've used the diagram to explain the concept of this digital computer. Any question? I have all these things. Any question? Any question? Any question? Any other question? Before I summarize what we have done, any other question? Then we close the session. Any other question? Any other question?
So about the digital and the previous one, the analog and digital. I wanted to ask if the walkie-talkies, which one did they fall under?
If what?
The walkie-talkies, which one do they fall under? Like with the analog representation and digital representation.
Okay, so what do you think yourself?
It's we have some which are digital and some which are analog. So with the signal types, that's what I wanted to know.
Okay, who again? The walkie-talkies, are they analog or digital? The walkie-talkies, are they analog or digital?
Analog, but some too are digital.
Some
I
are
don't
also
know if
high. Yeah, that's what it's true. Some of them are analog and some of them are digital. So basically, so the traditional ones are simple, the analog ones. You understand? So it also uses radio waves to carry, voice from one person to another. If we want to go through the process, the human voice starts as what? Analog. And in the traditional walkie-talkie, the voice is transmitted as what? Analog radio. So we have voice, we have microphone, then we have what? That of the radio. Understand? So the traditional walkie-talkies are basically what? Analog. Then the modern digital walkie-talkies are what? Are digital. So it depends on which one you are talking about. Once you appreciate the fact that we have digital ones there, then the digital ones are digital walkie-talkies, and the analog ones, which are the traditional ones, are also analog walkie-talkies. So walkie-talkies are commonly analog, especially the traditional ones, but the modern ones are all what? Digital, because they convert the voice into digital data before transmission.
Okay, thank you, sir.
Okay, any other question before I conclude the class? Okay, so now today we have introduced you to the basic idea of digital electronics. We have seen that electronics deals with the behavior and the movement of electrons, while digital electronics focus on circuits and systems that can process information in discrete forms, mainly zeros and ones. So we also compared analog and digital quantities. We said that analog quantities vary continuously, and we gave examples as voice, temperature, current, speed, and all that. We said digital quantities changes in step, such as in terms of digital watches, counting machines, and all that. We also discussed why digital systems are widely used. because why? They are easier to design, easier to store information more accurately, less affected by noise and all that. However, you must also remember one important limitation, that the real world is analog. Therefore, the data systems often needs to convert analog into what digital form. It needs to process the information or the data, and sometimes it needs to convert the digital output back into what? Into analog. Then finally, we spoke about the logic families and the basic functional unit of digital computer: the input, memory, the control unit, the CPU, and the out. And these units work together to receive data and process it, store it, and also produce a useful result. So the main lesson for today is this: analog means discontinuous in nature, digital means what? Discrete. And digital electronics is the foundation of the modern computer systems, phones, communication system, and so on and so forth. So for the next class, what we will do is that we will do a small recap on the difference between analog and digital, the advantages, the functional unit. Then we will move on to binary numbers. Move on to binary numbers. Move on to binary numbers. Any question? Any question? Any question? Any question?
Sir.
Yeah.
Yeah, since you said the real world is analog.
Analog, yeah.
And then so since analog systems, they do not have to convert. I mean, they don't have to convert to, let me say, discrete before back to analog, but digital system have to convert to, I mean, digital before back to analog. Is it safe to say analog systems would be faster than the digital system?
No.
The conversion is going to require some time or something like that.
No, analog systems are not faster than digital systems. You understand? They are not faster. What we are saying is that our voice is purely analog. Our voice is analog. But the processes that it goes through is digital. But because at the beginning it is, let's say, if someone is speaking, my voice is analog. But then if I call you, your mobile phone is a digital system. You understand? And it cannot operate on analog. It is digital. So it means that it first needs to be converted from analog to digital. So the phone converted from analog to digital. Then the output, what is sound? Because if someone is speaking, as I'm speaking right now, you are hearing my voice at your end. So my voice at your end is analog. But the process that it is going through, what is your mobile phone, that process is digital. You understand? Digital systems are always faster than analog word systems. That is the reason why we have transitioned from 1G, which was purely analog. 1G systems were purely analog. They were slow and all that. Now, currently, we are using 4G. Even when you go to the advanced countries,
it's 5G.
5G. In Ghana, you are using 5G.
Yes, we have some phones with 5G networks now.
But that is provided it is true. You understand? Provided it is true. Whether it is because I've not heard, is any of the telcos deployed 5G?
We can answer that.
Yeah, you can have.
America.
This class, yes, but the MTN, they have the 5G. And they deploy the 5G.
They've deployed the 5G. Okay, that's fine. Okay, so the digital systems are much more. They are faster as compared to the analog. Now you don't mostly, even all the cars that are coming, we are having a lot of digital, stuff in them. The analog systems are gradually fading out from the system. Fading out from the system. Good. Okay.
And say with this session too, I took some a certain lesson from it. Now I understand why in your radio you have a magnet in it. because of the radiomagnetic wave. Yes. So when you were talking about it, I was like, wow, wow, wow,
Yeah.
wow.
That's also another very good observation. Yeah, good observation. Okay. All right. So if we don't have any other question, our time is up. We'll end here. Then hopefully next week we will continue. I believe you have the slides on the LMS. I believe you have the slides on the
Yes,
LMS.
please.
Okay, good. So
Yes,
kindly
Yes,
try
please.
that's good. Kindly
We
try your
have it.
possible best to at least read something before we come to class so that our interaction and also discussion will be very, very good and you get to understand more of this concept very well. All right. So I'll leave you here. Then hopefully next week we'll continue. Enjoy the rest of your day and take care. Bye.
Yeah. All right. Thank you, sir. Richard, kona ko accept you.
Safi na ɛka saa de no.
America.
Safi, why na ɛgye wo yere kaa no?
Hello.